Okay, welcome to this webinar on the series of the E39 webinars that we have. This session is being recorded for your information. The people who are listening in on this webinar will not be in the recording unless they actually say something. Today's webinar is being held by Henrik Skyvulstad, who is a PhD candidate at the Norwegian Technical University in Trondheim, and he's also working in Norconsult. The topic for today is wind tunnel testing and nonlinear load models for extreme bridges. So, Henrik, whenever you're ready, please go ahead.
Thank you, Matthias. Yes, so like Matthias said, my topic for today is wind tunnel testing and nonlinear load models for extreme bridges. Okay, so short introduction of me. I'm full-time employed at Norconsult. I'm an industrial PhD at Norconsult and the Statens and the Research Council of Norway is paying my salary, and the Norwegian Road Administration is paying for the research funds. So it's a 4-year position with 1 year mandatory work at Norconsult. I have a fair amount of supervisors, actually. I have Ole Øyseth as my main supervisor, and I have some academic supervisors, Anders Rønquist and Roberto Sasso from Politecnico di Milano. And I have some internal supervisors at Norconsult, Alexander Skyte and Jon Solheimsli. So my progress is that I'm more or less 9 months into the PhD with 4 or 5 months of taking classes. So I'm not that far into the PhD, so it's going to be more of a presentation of future work than and results. We have some preliminary results and some guidance, but they're still not we're still not completed yet. So I only have 1 conference paper that I've published, so that's why. And for in-depth results on the previous work, I recommend watching Bartosz Sidziako's webinar. Also in this series, he's been couple 3 months ago, he also had this webinar. Okay, so the motivation, I'm going to talk, or a short overview of my talk is going to be a motivation, some research methods, short and simplified wind course for load models, and some results and future work. So let's go. So of course the Ferry 39 project is the main part of the motivation. I'm not going to show all the slides about that project here, and most of you know a lot of the project on the forehand. But for my point of view, the expansion of the suspension bridge concept from 1900 meters to up to 3,700 meters, it's really interesting. We know that for increasing the, if we increase the span width, the flutter instability limit decreases, and you can see you have some examples here with a live fuel bridge that we did not long ago. It has 140 meters, and the Hardanger bridge that's 1,300 meters. That's a bit longer. It has 67 meters per second and flutter wind speed, and the Sognefjord bridge is so much longer. So what is the flutter instability limit going to be there? It's really critical. And if you use same cross sections as for Hardanger bridge on the Sognefjord bridge, it's probably not going to be okay. So then people have decided to use twin decks or even triple decks cross section. This is a twin deck cross section here, and it's kind of new cross section. There's not many bridges that have been built with this cross section, so this needs to be researched properly. And on top of that, we have a lot of uncertainties in the wind tunnel. An example here is from the Hardanger Bridge. It's two different wind tunnels. But it's really easy, like a standard test of doing. You can see that there are major differences in the static coefficients from these wind tunnel tests. So it shows the gap or the lack of precision in the wind tunnels. And on top of that, if you consider that the Bjørnafjorden has 65 to 80% of its design stresses from wind and wave, is that much. And you see, if you have so much inconsistencies in the test, of course this is wave also, this is going to be a major concern for the price and for the safety of the bridge. And Antonio also has a newly developed forced vibration rig that tries to handle this problem. So if you see on the global scale, you see the whole wind system. You have a global weather system that's big big storms, and the meteorologists' way of seeing it. From that you get the main wind direction and the mean wind velocity. When the mean wind velocity and the main wind direction hits the local topology of the bridge site, it creates eddies and turbulence and basically pressure that hits the cross section of the wind. And then when these pressures hits the cross section of the wind, you get different kinds of forces, dynamic forces that has its own correlation, and has admittance. You need different load models to handle that. And then when you have the dynamic forces, you take these forces and do a dynamic calculation of the bridge with its the stiffness and damping and the mass matrices, and you get response. Then you take the response and you find stresses, and then you do the design criterion with different codes, and then you find the dimensions, and then you do another loop to redo that aerodynamic forces and stuff. So if you see, I guess the zoomed version of it, if you have the wind pressure on the left side, and then the aerodynamic transfer function, wind loading, and the dynamic transfer function, and then response, then you have the motion induced forces. Because of the motion of the bridge changes the wind load again, so the aerodynamic transfer functions need to be updated. So this is basically what my PhD is about, this aerodynamic transfer function and the motion induced forces into that. So it's basically a fluid structure interaction converting wind pressures to loads. Now it seems kind of simple, but it's really not. Here you can see some of the on the top right here. This picture kind of shows the complexity of the problem. This is just a normal flow out in a stationary fluid, and it looks chaotic because it is chaotic. Turbulence is really hard to model. You can see the difference in when you have the tap, water flowing out of the tap. This is like almost fluid laminar flow. It looks simple, but when the turbulence gets into the system, it looks really messy. And that's because you have so much dependencies. A small particle on the top here needs to it's in relation with a particle here. You have a lot of fluid memory, and it's highly nonlinear system. So we have different methods of solving this. You can do the analytical approach, then you have to solve the Navier-Stokes equations and have a stable solution of that. If you do this, you're a complete genius, and you have solved one of the 7 millennium problems, and you receive $1 million from this math institute. And maybe you win a Nobel Prize, I don't know. But this is not my approach. You can do CFD modeling. It's more or less finite element for the structural engineer to understand this, is kind of finite element methods for fluids. It's really CPU heavy if you're trying to include a lot of details. But it's a viable method, and at our research group, Tore Helgedagsrud, he's doing this approach, and it seems like it's more complex for twin deck sections because of the turbulence downstream hits the next cross section. But yeah, we can wait for his webinar to see his results. So that's the last approach is the wind tunnel testing that I do. We test the cross section in the wind tunnel, and we try to fit mathematical models to this, or simplified mathematical models to this to the test results when you measure the input and output. So then we have different kinds of wind tunnels. You can see wind tunnel tests. Sorry, you have the full aeroelastic model test. Where you actually build the entire bridge with cables and hangers and stuff, and you need this. I guess this is like 14 meters wide, so you need a really big wind tunnel. And it's very hard to extract the coefficients from this. It's more or less complete design to see if everything's okay, and when you're finished, kind of. And it's really expensive to do. And you have other more easy tests when you only test the bridge cross section. You have this free vibration setup when you suspend the cross section in springs, and you have a mass system, so you can calibrate. You can get the two eigenfrequencies in this vertical and torsional eigenfrequencies. You can see that this is a test done at Sveinung Ole Hansen in København, and this is a test to show that we can get flutter instability in the wind tunnel. This is cheap. It's less precise, at least in some points. It's necessary for if you want to check vortex-induced vibrations, but yeah. But you need to include some load assumptions to get the aerodynamic derivatives and stuff. So it's not easy to see the nonlinear forces that I'm interested in, and that you should look for at least for twin deck sections. And then we have the force vibration rig. It's basically fixing the section model in motion arms. Then you force the motion in the motion, force the cross section in the motion that you pre-describe. And then it's some parts gets easier. It's a lot easier to handle the nonlinear forces, to see them, and the precision of the system is varying from system to system. But we at NTNU have a really precise system, and I think it would not be a bold statement to say that it's the state of the art. This motion-induced or this force vibration rig we have here. Okay, so what we do is what our force vibrational rig looks like. It looks like this. You have 6 internally connected servo motors that force the system in a very precise manner, and then you connect the cross section via load cell to get the forces. And here you see the total setup. So you measure the forces on both sides of the bridge, and then you have what you want basically. But all the tests are done with first without any wind speed in the wind tunnel, and then with the wind speed in the wind tunnel. So to get the forces, we subtract the inertia forces from we call the still air tests, and then we have everything we want. And we have a selected working range that we've been working on until now between 0.1 to 3.5 hertz and 0 to 14 meters per second, and we have mainly been testing in smooth flow. We have opportunities to do other stuff, but this is how far our research has come now. So we can expand this working range, I guess. So this is basically my PhD. We're measuring the turbulence, the mean wind in the wind tunnel, and the motion on the cross section. Or this is our pre-described, and then we measure the forces that comes out of the system. Then I'm trying to find a suitable mathematical model to link the two together. So we have 3 levels of mathematical models. You have the existing linear load models, quasi-steady theory, and aerodynamic derivatives. It's easy to understand, but the precision can be low, at least if it's nonlinear. Then you have level 2, we have fairly new nonlinear models with Volterra series, relogical model, band superposition model, and hybrid model, and so forth. And they have level 3 that has a more black box machine learning algorithms that basically it's the physical meaning is there. The model that doesn't have any physical meaning, but it can be really precise. So the goal of the PhD is going to be to find and develop models that are useful for actual engineering and for the Ferry-Free E39 projects. Okay, so short, simplified wind course. It's not, yeah. Some parts are left out just to make it clear. If you consider a beam in space with submerged in a fluid and the wind, or the wind fluid, or the air, then and you have a wind going in from the left side with an angle, you can measure the forces, horizontal forces. It's when you measure this, you have these static coefficients that depend on the angle of attack that gives you the force, basically. This is still and without turbulence. And then we have, so this is a static force. Then you have a turbulence. The turbulence changes the mean wind velocity. You have the delta V here, and it also changes the angle of attack. So now we can calculate the forces from turbulence as a change in angle of attack and a change in wind velocity. Then you have the third part of the wind force. You have that the cross section now is not standing still; it's actually moving, and this has an actual change in the relative velocity of the cross section and change in the relative angle of attack of cross section. So this you can also find the motion-induced forces, or the motion-induced forces, or self-decided forces from this simple equation. And then you want the total wind load in the horizontal direction, you sum the 3 up. So this is basically quasi-steady theory in a really simple manner. So, but isn't that okay? No, it's really not, because this is imprecise for motion that are not really small, or change in turbulence that are not really small. It's not any memory in the system. It's a linear theory that needs superposition to work, and it's unable to predict flutter instability also. So it's not good. So we have this improved model for the turbulence. We have introduced something called the aerodynamic admittance functions. It's basically a function that's saying that if the frequency is really high compared to the structure, that the turbulence frequency is really high, then the forces you get on the structure is less. It's like thinking about a boat. If a boat is really long and you have a lot of short waves on the boat is not going to feel the actual force. But if it's a long wave, the boat is going to be, it's going to feel it much more. And the aerodynamic derivatives is frequency dependent, or usually frequency dependent. And then also introduce aerodynamic damping stiffness matrices that's not only depend on the static coefficients. It's actually a frequency-dependent aerodynamic derivatives. We'll see what that means later, but introduce more improved version of this part. So, but then you still add the three effects together, and it's still a linear load model, and it's all converted into frequency domain. Okay, so a bit formalization of the theory, the linearized quasi-steady theory. So if you consider smooth flow and we remove the turbulence part, we have two forces on the cross-section. You have the static part and you have the motion-induced part. And the static part we keep, it's okay, but then we need to handle the delta mean wind velocity and the delta angle of attack. And then we introduce some assumptions to make the theory linear. We say that the static coefficients is linear around the mean angle of attack. It's not changing a lot. And then we take the higher order terms and say that these are neglectable. And then we get a linear theory down here. So the R and R dot is the velocity of the cross-section and the displacement of the velocity of the cross-section. Then we get these aerodynamic stiffness and aerodynamic damping matrices that has the derivative of the static coefficients in them and the static coefficients in them. So this can be found only by testing, doing static wind tunnel tests. This has the same assumption as I said before. It has to be small rotation, no memory, and it cannot predict flutter. And then some people in the early 30s, 40s, they did found analytical expressions for ideal flat plates in potential flow. Basically mean that no turbulence and so like ideal situations and no bluffness of the body. And then they found that you can find these motion-induced forces by introducing frequency-dependent, reduced frequency-dependent factors. And Scanlon expanded this framework of. He basically said that okay, we need to fill entire stiffness and damping matrices with this frequency-dependent. Aerodynamic derivatives, and he's not saying what this should be, but we could test it and find to fill these matrices. So now that's how we came up with aerodynamic derivatives, and it's been working very good. And you need a dynamic test to validate or to calibrate these models. And this theory is widely accepted for single box girders and for linear cross section, and it's been used also for twin deck girders. You can transform this into time domain by fitting Fourier transformable functions as rational functions or additional functions. That's no problem. But it's the theory is still a linear theory with now it has some linear memory put into the system because of the Okay, and okay, so that was a bit theory. Now over to some published results, mainly by Bartosz. He has been doing single harmonic motion tests to find the aerodynamic derivatives of the Hardanger bridge, and then he did biharmonic motion tests. He tests two harmonics at the same time, split them, and tried to check if the superposition worked. And then he did some identification of the rational functions. That's not so important in this manner. But he mainly tested the Hardanger bridge and did some tests on the twin deck sections. So here we have some of the results from Bartek, summarized in one page. You see that the aerodynamic derivatives that are important, the vertical torsional ones, they are really, really linear. You have almost no scatter, and this 4 here and 4 here. And you see, from this we have concluded that the rig works very well. We have worse drag performance, but that's mainly, I think this is because of the drag is less linear because of the shape of the static coefficients. And also it's less forces, so it's hard forces compared to the motion-induced forces is small compared to the actual forces on the cross section, so it's higher, gets a higher inaccuracies from there. And another conclusion he had is that the Hardanger Bridge cross section behaves very linear, so we didn't need the fancy linear, non-linear models that I am trying to figure out how to use. Okay, so the one and only thing I published yet is a conference paper. There we tested the harmonic motion for the twin deck section, and we found both good and bad estimates using the aerodynamic derivatives. Here you can see an example of a good estimate that the aerodynamic derivatives predict the self-excited forces very good, but we also have bad measurements here, you can see. Then we took this this force, the self-excited forces here, and took the spectral density of that force. You can see that this is the motion frequencies of the cross section, and it should be only one frequency that are predominant, but you can tell that you have superharmonics on the double that amount of frequency and 3 times that amount of frequency. And we also plotted the hysteresis behavior. It's basically the behavior of the static coefficient dependent on angle of attack. If the system is linear, you should have clear elliptical shapes here, but you can kind of tell that these are not elliptical at all. This tells us that this is actually, we think it's a highly nonlinear cross-section. So another way of telling it is, as I said, single harmonic input, multiple harmonic outputs, superharmonics, non-elliptical shapes, non-linear relation between amplitude. It basically means that if you double the amplitude, you should double the forces. Sometimes we can see in the literature that if you double the amplitude, you have 10 times the forces. And the superposition is not working, and they may exhibit properties such as limit cycles and bifurcations. Okay, so why is the nonlinear forces a problem? If you don't consider them and it's high nonlinearity, you really don't know what's going to happen. It's basically unpredictable. If it's it can alter the system to be better, but it's also it can also alter the system to be much worse. So in my point, we really need to have control of these nonlinear effects, at least for twin deck sections that has been showing much more nonlinearities than the single box cross section. So an example of this could be, for those of you that are familiar with Flutter, Flutter is a coupling effect between the vertical and torsional motion of the system. When you increase the mean wind, suddenly you start to get almost no damping in a coupled motion between vertical and torsional. But our cross section, the twin deck cross section, basically says that at some frequencies, 1/3 of the energy in one harmonic is dispersed through superharmonics. But what happens if the superharmonic or the torsional frequency has doubled the frequency on the vertical motion? Then you get then you get from the vertical motion, you get excitements in the torsional direction. This is not unlikely to happen, and we don't really know the case. And that's just one example of what I thought about yesterday. What can happen if we don't have control of these nonlinear problems. Okay, so my ongoing research, we're trying to fit nonlinear models to the twin deck I've shown from the conference papers. There are a lot of models from Teng Wu and Karim, and Polytechnical di Milano has suggested some models. And then we're trying to standardize the force, a procedure for force identification, nonlinear force identification. And we also have a couple of other cross sections that we're testing. Some master's students have tested a suggested cross section for Bjørnafjord, and I'm sorry, and this yeah, tested from from Sulafjord. Sorry, really messed me up there. And we also have our own cross section with detailing that we are going to test. So then we're going to have 3 different cross sections. I hope we have some way of concluding then. Okay, so short introduction for different nonlinear models. We have a rheological model or a hysteresis model. It should have been say. It basically is, you know, the way the static coefficients is dependent on the angle of attack. And then the hypothesis of this model is basically to push everything into a dynamic angle of attack, the motion on the cross-section, the rotational motion on the cross-section, the vertical turbulence, and the vertical motion. And you have this one unique parameter to play with. So this basically reduces the total system of being dependent on all this to a much easier system when you can curve fit your forces on dynamic angle of attack and the velocity of the dynamic angle of attack, and you can basically curve fit these in higher polynomials or a rheological dashboard springs fancy system. This can work, but you have to have don't handle strong nonlinearities. Hopefully we don't get strong nonlinearities either. We want cross-section that's mainly linear. It's also easy to overfit the problem, and now you have equal contributions from the vertical motion, the vertical turbulence, and the rotational motion. We don't really know if that hypothesis is valid, and yes, and maybe it's too simple to push everything into one dynamic angle of attack, one unique parameter. Okay, so Diana suggested a new model or another model. It's called the band superposition model. It's basically we split the motion induced part and turbulence part into a low frequency and a high frequency motion, and then you take the low frequency motion, you take the quasi-steady theory, not linearized quasi-steady theory, and then this gives a base motion, and this basically gives a base angle of attack. And on top of that, you use the aerodynamic derivatives and admittance function on that angle of attack. Say your cross section is varying really slow, and it has like 2 degrees compared to the wind, and then you take aerodynamic derivatives that's all tested on the 2 degrees angle of attack, because the aerodynamic derivatives changes also in compared to the angle of attack. So, and then you just sum up the 2 contributions together, and you can see on the figure on the right here, they've tested, they have a slow harmonic. They took a slow harmonic first, and then they have a fast harmonic also, and then this is basically, and then if I see the forces are really varying depending on where the slow harmonics or what angle of attack the small harmonics give. So this is basically this is a linearized version of it has some linearization, time linearization compared to the angle of attack. This model is it's good because we know these are all known theories and kind of valid theories, but it also has clear drawbacks. It's not easy to know what supposed to be low frequency and what is the high frequency band. And the hypothesis also suggests that the angle of attack is the only parameters that's important for the nonlinear system. Okay, so over to another more mathematical model. This is the Volterra model. It's basically expansion of the linear convolution integral. This is known from if you have a basic course in dynamics. So you have the impulse response function, and then impulse response function, and then you have impulses. You basically integrate the impulses in time. It's how you handle in time domain single system with or a dynamic system with random motions. And if you expand this this way of thinking into more handles more impulses. If you say that one impulse affects another impulse that are I guess a second later, you get this two-dimensional motion impulse response functions, or Volterra kernels, that is called, and then you can expand this in 3 dimensions, 4 dimensions, and stuff like this. This is a more mathematical approach, and it's guaranteed convergence if infinite order of the motion is applied, and it's also it can be seen as a Taylor series expansion with memory because you have higher and higher order. But this is mathematically good, but it's really computationally heavy. You get tons of it's almost unusable for higher order than 3. And is that enough? How many do we need? We don't really know. And the identification procedure is kind of hairy, I think. It's basically a hard model to calibrate. And the last model I'm going to show you, it's an artificial neural network model. It's the black box machine learning model that's very popular these days. It's the architecture is you have input layers with nodes, and then you have connections through a number of hidden layers, and this also gives over to another output layer. So if you see if you zoom in one single neuron, you see that you have a lot of weights going into a transfer function. And then if for example, this is an example of a transfer function. If the sum of the weights is more than 1, it triggers a signal further. So it triggers the weight to the next neuron. So the way this system optimizes itself, it's by changing the weights. So the change in weights give a change in the output, basically. So you do like a simple chain rule and find the chain rule optimization and find the part where with least energy. It seems complicated, but actually it's not that complicated. And for both in Python and in MATLAB, we have well-developed toolboxes that you can train your system, so it's actually pretty easy to do. And but the physical meaning of the weights, it's impossible to understand. So you lose the physical meaning of the problem basically. And the system was also, but the system there is very flexible. It can be, yeah. If you don't have any clear idea of how to fix a problem, it's easier to just make the computer, or I mean, I'm saying on like to be funny that we just throw data at the problem and the computer fixes the problem by itself. It's not really true, but it seems like it seems more like it in this way than in the Volterra series models. Can also include a lot more input than only angle of attack, so that's also good for this model. Okay, and we also have other types of models. I'm not gonna go into these in details, but okay. And then we have an overall goal of the PhD is when to use nonlinear models and develop some of the models further, standardize the identification procedure, trying to validate some of the models, and recommend models for engineering purposes, I guess. So I'm trying to do some guesswork and see what's going to be the conclusion of my PhD. But now it seems like the nonlinear models to go for is the neural network model or the band superposition model. Neural network model is basically it's user-friendly and it's really flexible. And the band superposition model is expansion of the known framework, so engineers know the aerodynamic derivatives and also should know the admittance functions. But it's really important to validate these models. It's you can be way off if you're not really careful. It's really important to have independent data for validation. And to be honest, can be really hard and really frustrating to use these models. At least from now, hopefully we can find more standardized procedure to do this. But it's really a kind of a specialist's job. You need to be trained in these models to be able to work with them. And last slide, we have some recommended of choice of cross-section. In my opinion, we need to include if the cross-section is linear or not into the criterion of choosing cross-section. We have criterions of avoiding vortex-induced vibration, reducing the static coefficients, and have a high enough instability limit. But this should also be included to try to keep the cross-section as linear as possible. The probable causes of the nonlinear forces is that the downstream deck gets hit by really high correlated turbulence forces. So basically the turbulence gets really correlated and kind of abrupt turbulence, and it gets the downstream deck, it gets really high forces from these turbulence components. And then you have an irregular flow pattern through the slot. So if you try to keep the cross-section streamlined and pay close attention to the flow in the gap, that's really good. And in my opinion, you should try to avoid curved cross-sections, so you don't have to deal with the Reynolds problems on top of this. I think, and Messina Bridge had curved cross sections, but I'm not sure if they would use that now. Later, you can use the nonlinear forces for your advantage. I'm not saying that it's bad. I'm saying that it's unknown. It could be much better for if you have control over it. You could reduce a lot of problems. And then, so how to identify some of the nonlinear forces is, I recommend using force vibration measurements and taking the FFT of the forces and see if they have superharmonics. And look at the trends in there when you have identified the aerodynamic derivatives. Look at trends if you see that clear have more trends than just one clear path. Plot hysteresis as shown today, and if you should check a wide range of amplitudes of angle of attack and see if the structure or the cross section is nonlinear here. And it's important to remember that it's not only the rotation of the cross section that gets an angle of attack. The mean angle of attack from Hardanger Bridge from the mean wind velocity, it's actually 3 degrees, and that's a lot. And you should test on 3 degrees also to see if you have nonlinear. Maybe you should test 5 degrees. I don't know, but you should test not only 0-degree angle of attack. And if you a way of indicating that you can have nonlinear forces is if you have abrupt changes in the static coefficients. This is static coefficients. I think this is a Messina bridge. But if you see places where the static coefficients changes or the derivative is high, this could indicate nonlinear forces. This is really smooth, but you could kind of tell that when you're here, this is a 6-degree angle of attack. Here it could be a lot of nonlinear forces, and also maybe here. That's just recommend. Yeah, you should try to keep the static coefficient smooth if that's possible. Or yeah. Okay, so that was all. Thank you. So if you need to contact me, please use this mail, and you can also, please, if you have questions, just...
Yeah, thank you so much, Henrik, for a really good presentation. I really enjoyed the part that you also had some clear recommendations for us at the end. Well, as Henrik said, if you have any questions, we have plenty of time at the moment. So please come with any questions if you have. You can also write the question and I can read it up.
Hi, Henrik.
Hi.
Maybe I have a question for you. Can you hear me?
Yeah, I can hear you.
Okay. So these mathematical models, they, as you described in one of the slides, you get the input, turbulence, mean wind, and the motion of the section, and they tried to predict the forces and the pressure distribution, right?
No. Yeah.
But these are very case specific, I would think. So for two different cross sections, they're completely different. Would that be right?
Yes. Of course, the input and the output of the from the wind tunnel it's different, but hopefully we try to get mathematical models that can fit more cross section. But of course, a mathematical model cannot be used with that with a calibrated mathematical model that you use for one cross section cannot be used for another cross section.
Exactly. That's what my the question was going is, could that be included in these neural network algorithms? Would you think that if you would, for example, change a small parameter like the distance between twin girders, do you think that would just increase the complexity so much that the machine learning wouldn't catch the logics of it, or if it could actually catch and it be a very useful tool for the design and optimization?
I think if you train the neural network on one gap width, and then you use these weights for to train on less data, it would be the training procedure will get much faster. That's one part. But I think you could also it's really hard to know, but I think you're less off than just guessing. But I'm not really sure if...
Yeah, definitely. It's too early for that, but I was more wondering if it was considered at all to include such a design parameter on the cross-section shape.
Yeah, of course.
In the latest stage of your PhD with the...
all the cross section has you can vary the slot between them. Of course, we can test that, but we are considering the neural networks as individual neural networks for different cross section.
Yes.
Basically, that's how that's answering your question.
Well, we have another question here. I will read it up. But you can also read it, Henrik, silently, but I will read it up for the recording. For the NN model, the model requires the models to be trained for a particular kind of data. what kind of data sets would you train your models with? How flexible would these models be when you change the underlying design of the bridge? Example, when you change a model trained on suspension bridges for a suspension bridge on floating foundations. So I guess it's sort of in the same way, similar to the questions that Bernarda just had.
Yeah.
But here we're also looking at how does the fundamental dynamics or the modes, when the modes shape change, how will that change the relationship?
Okay, so in our force vibration rig, actually the eigenfrequencies of the actual bridge is not considered. We're just trying to cover a wide range of the reduced frequencies. So the way that we will train the neural network would probably be to have random motion going from low frequencies to pretty high frequencies, and then we're of course going to validate on another random motion test. But when we cover a wide range, this neural network is cross-section shape dependable. So you can use that cross-section on a suspension bridge or floating suspension bridge. Also, it's this cross-section specific, not specific to the type of the structure.
Hi, sorry, that was my question. But what I wanted to ask was, so for example, when you shift from a suspension bridge with fixed foundations to a floating one, for example, so then you have extra hydrodynamic loads coming on to the system. So will I'm guessing once you've trained your neural network for a certain kind of bridge, then you can only extract data for similar kinds of bridges. You can't, right?
Yeah, the way that we are thinking about training this neural network is you get turbulence or basically wind pressure on the cross section, and then you get that's input, and the motion of the cross section as input, and then the force is output. So this is it's actually independent of the dynamic system of the cross section, as long as we have calibrated the model to include different kinds of motions. As long as the motion from the floating bridge is inside our validation area, it doesn't matter. So it doesn't matter what the actual damping of the system really is, as long as yeah, I can show you. Maybe that's easier to. Okay, so here you have wind pressure here, and then you have a transfer function, and then you have the response. But if we consider a wide range of wind pressure and actual motion, and train it on this, it doesn't matter what kind of dynamic transfer function we have, as long as it's inside the training bounds. So yeah.
And then you would validate it with numerical model, like normal analysis that we do for bridges, for example.
Yeah. You could. It's basically the way I would take the neural network. It's basically like quasi-steady theory. It's the wind pressure in time series from the wind pressure in on the cross section, and you have a motion on the cross section, and then you get the actual force on the cross section. You take the force on the cross section, put that in, say, abacus, and then you get a new motion, and then you get a new force, and then it's still, it's the same way. It doesn't matter what kind of bridge it is, basically.
Okay, thank you.
Hello. Hi, Henrik. Can I ask a question?
Yes.
Yeah. Thanks for your interesting presentation. Because the title of the presentation is about the wind tunnel testing of nonlinear load model for extreme bridges. Have you considered that to include like floating bridge in the model test in the wind tunnel? Because that is what I think also quite interesting. Of course, then it comes in the wave flows and so on. But is it a plan? Is part of the plan for this wind tunnel test planning?
Not for my PhD project. I know they have been working on Politecnico di Milano has been working on this hardware in the loop with a floating wind turbine. And I think there have been talks about how if we can combine efforts, but I'm really sure if how the progress on that research field is about. So I don't know.
Yeah, because I think there might be other presentation related to this, or I don't know, because I thought I was reading some of the presentations are about this kind, but yeah. But one more comment about this. Can you go to this wave from boat effects? That slide. It's out of your presentation scope. But for this effect, I think it's not that the ship is not feeling anything, but it's feeling something that we cannot feel. Do you think so? Because I think the response that the boat can drift away if the waves is short, right?
Yes. This is just
that's just the
presentation of to get some physical understanding of the problem. It's not correct. Of course, if you have wave drift, the boat will drift away. But that is not. This is basically vertical. You cannot feel the vertical. You cannot feel the vertical motion from the waves if the wave has really high frequency. Basically.
Yeah. Okay. Yeah. Thank you.
Thank you. Any other questions?
Maybe I have one more quick question just for curiosity. On twin girder decks, have they ever been attempted to be solved instead of one cross-section as two cross-sections, so that the second cross-section has an input that quite complicated, I see it, but has this been ever attempted that it would be completely different?
Actually, when we're building our new cross-section, I haven't included this in the slide because it's kind of a new idea, but we are mounting. Do I have any good picture of this? We are mounting. The load cells on both of the decks, so we can see what force comes on the other deck also separately. So there I can see. Yeah, I don't have this at the moment, but from there we can see if the force, what the forces really look like on the downstream deck. I've seen some work done on this by the pressure taps. We have pressure taps around both decks, and then you can kind of tell why the nonlinear or where the nonlinear forces are coming from. But these are done mainly on static coefficients, not on dynamic tests.
Not on dynamic.
No.
Because if you would find a linear correlation on the movement and the angle of attack of the first girder with the wind forces on the second girder, if you could find some linear relation for the different frequencies, then this could be a good explanation for many non-linearities. But I'm not sure this is certainly many other difficulties in the process.
Yeah, Yeah, it could be that it's possible to find a relation that maybe the turbulence has super harmonic frequencies, and that hits the second deck, and that's why. So you could kind of have this coupled. You can maybe it's possible, but I don't know yet. So it's
Thank you.
not a bad idea.
It's a good presentation. Thank you.
Thank you so much. Are there any more questions? I see that we actually are running out of time now, but before anyone else asks any questions, I would just like to remind people that the next webinar in this series will be October 5th with Mikael Sterk-Andersen on bridge area elasticity and the non-fluttered design principle for long-span bridges. So as you can understand, we'll continue with the topic theme here on long suspension bridges. Okay, anyone think we'll open up for one more question if someone has? Okay, well, in that case, I would like to thank Henrik for a really nice presentation, and I'm really glad that we got an interesting discussion in the end here. There is a lot of exciting work going on regarding at least twin deck suspension bridges at the moment. We have the new suspension bridge under construction in Turkey, which has just undergone, where the design has just undergone full area elastic wind tunnel testing in China, I believe. And we also have work that's been done on with Sven Ole Hansen with regards to the studies the road directorate is doing on twin box girder for long bridges. And of course, we have all our fantastic PhD students at NTNU and other universities studying these phenomena. So there's really a lot of interesting things going on. So once again, Henrik, thank you so much for your presentation.
Thank you.
And I think we can stop recording now. Kjersti.